So next we have Isabel Medlock. Oh, the microphone. She'll hold the microphone. So we will continue the theme of probing the cosmic, well, web or CGM with fast radio bursts. So thank you so much, Isa.
Can you hear me okay in the back? My name is Isabel Medlock. I am a rising social science student here working with HiPACC, and today I'm going to talk about projects I've been working on using FRBs, so astrophysics technology, specifically using CAMELS. Basically, for this talk before, but basically we're interested in the effects that baryons have at various scales. So this plot shows the ratio of transition over the corresponding n-body only simulation, and if the simulation behaves exactly the same, that ratio will be on scales dotted pattern. The simulation is chosen case, and depending what simulation you use, eagle, electric, sigma, and so on, the degree of suppression at different scales varies. It's the ratio of the amount of power versus and in particular, we're interested in two areas, Milky Way like halos, baryon cycle and CDM, and then more broadly, cosmological parameters, specifically the S8 tension, that weak lensing, Matt Gebhardt in the CAMELS simulation recently put out a paper measuring the spread metric, which was first introduced by Jeff Burrow in 2019. And basically, the spread metric simulation is the distance that a particle will spread between initialization all the way to zero, and the nearest dark matter particle. And this can be measured through both gas particles, baryonic particles, and dark matter particles. Simulation, so Matt showed that this normalized spread, gas spread over matter spread, is a very good proxy for identifying the degree of suppression at scales below, say, of the matter power spectrum. So it's a very promising quantity. The problem is that this quantity and other similar quantities, which are the same halo baryon fraction that have been proposed, are either impossible to actually observe or very challenging to observe. So this necessitates simple, straightforward, and clean observable. And that brings us to FRBs. As Greg said earlier, FRBs are a relatively new probe, first discovered in 2007, when Lauren and his grad student were looking through archival pulsar data. They found 6 FRBs. And now, several years later, almost 20 years later, we've detected thousands of FRBs. And we're excited about FRBs because the dispersion measure traces directly free electrons along the line of sight. The observed dispersion measure is made up of several components that we have to disentangle. So there's a component that comes from the Milky Way, with the ISM and the halo. There's a dispersion measure from the host galaxy, and then what's called DM cosmic or DM extragalactic refers to both dispersion measures of the IGM and any intervening halos. Specifically, I'm interested in looking at DM cosmic contribution for DM IGM and DM intervening halos. But there are several other models for DM Milky Way and DM. I think it's important to note that when I refer to DM Milky Way and measuring dark matter, which is something. I'm using the CAMELS simulations, which right now is a set of 14,000 simulations, 7,000 hydro simulations, and it's primarily designed for machine learning applications. So CAMELS right now has 10 different suites with 9 different subgrid physics models, including PNG, Simba, and ASTIC, which I use in the project, as well as an n-body suite. with corresponding simulations that match with the hydrosim. In addition to running these different models, they also vary 6 parameters in the original iteration. First 2 parameters that they vary in this iteration is omega matter and 8, and then they have 4 parameters relating to baryonic feedback, 2 supernova feedback parameters, and 2 AGN feedback parameters. So they end up in one T-set for which they vary only 1 parameter at a time, holding all the other parameters constant, about 60 simulations per subsuite, so 66 for CAMELS TNG, 66 for SIMBA, and so on. So I looked at those simulations in this project. To look at FRB sightlines in simulations, the first step is to make these dispersion measure maps over a typical simulation box. So this is just for redshift 0, traditional models that you see enacted. And just looking at the maps below, you can see the difference. In red, but the SIMBA map, here's a here, well, more, the baryons are being spread further away from structures. And that's reflected too in this distribution of the dispersion measure over the box. You can see the difference between the different models. In addition to that, we looked at dispersion measure halo profiles of halos in these boxes. These are radial profiles of excess or delta dispersion measure in comparison to the background dispersion measure we get from the RGM. So these are bin by halo maps for SIMBA TNG enacted, and median profiles across all of the halos that mapped in are shown in the black box with the pattern. And there have been some preliminary observations, such as the Rabi and Cook 2023 papers that measured the Milky Way dispersion measure of halos, comparing them, as well as the Ruin McQueen paper in 2022, which used a sample of prime FRBs to look at nearby halos, CGM, or dispersion measure. FRBs are typically found at large distances. I think there's only one that's been detected within the Milky Way itself. I think the furthest that's been detected or confirmed is redshift 1, but I think we do expect more for the redshift. So next step is to look at what these distributions and statistics look like for FRBs that are found at these cosmological redshifts. And this is for, again, the traditional models for a set of 10,000 FRBs at redshift 1, comparing celestial TNG with SIMBA. And there's a pretty clear difference in the distribution. SIMBA has the narrowest distribution, and we prioritize more uniform distribution of baryons throughout the similar boxes because of the higher AGN feedback, whereas Astrid has a wider distribution. The median and median typically slightly lower because, or slightly higher because of the weaker feedback overall compared to SIMBA, and TNG lies somewhere in the middle. The width of this distribution is something that we can characterize with a single parameter. So this is them apart, redshift dispersion measure relations that I showed at the beginning, where this gives the redshift, or the dispersion measure you expect from the IGN intervening halos as a function of redshift. So the colored points are actual observed FRBs, and this equation, the second equation gives what we would expect that means that distribution would be to the IGM, depending on what cosmology you choose, and this plot uses cosmology. We take a single redshift, we get a distribution, simply as a J-shaded area of dispersion measure, and the width of that distribution can be characterized by this parameter PS parameter. So that's the fractional standard deviation of dispersion measure equals S scaled by over square root of 0.5. So I measured F in the CAMELS 1T set. This plot shows what happens with measurement of F when you vary the 6 different cosmological parameters and astrophysical parameters in CAMELS. So for instance, when you vary omega matter, F is usually all 3 relations, It's also important to note that F scales inversely with feedback, so a higher F value, something closer to 1, means that there's weaker feedback, and a lower F value, closer to 0, is stronger feedback. So we've looked at recessive areas used as parameters, and we also compared against David Fusto's recent paper, where he took about 78 FRBs, 21 that are localized, which means they have both galaxies or redshifts assigned to them, and found a lower observation limit with confidence of 99.7%, and that's at after doing this calculation, we thought a bit about Matt's paper and the baryonic spread method, and we were curious what that looked like. And we plotted dollar F parameters against Matt's baryonic spread method, and we found that there was a pretty tight correlation between two pretty independent subgrid models. And we fit it with a preliminary exponential decay function. And then taking this, we've measured the matter power spectrum ratio directly by G over n body, and colored this ratio by F parameter. And you can see a pretty clear correlation between the degree of suppression in the spectrum and our evidence, especially as we roll with this. So it's something we want to work on more in the initial stages. Some caveats to the CAMELS project specifically is a very small box size, only 25 megaparsec, and our F parameters and dispersion measure variance are systematically skewed lower. So we need to repeat something like this on the upcoming CAMELS 50 megaparsec boxes, which are really the minimum of what you need for MD simulation and calculation, or other original PNG, Astrid, and Symbol models, or other suites like Flamingo and Crocodile, etc. Something else we're thinking about is how to best model FRB dispersion measures and simulations, like where should we start our sightlines, what's the best way, best practice for constructing sightlines. On the observational side, we need to work on, in general, in the field, uncertainties in dispersion measure models of the host and Milky Way, understanding if the F parameter is a constant redshift, which is what we assume and has been assumed before, but is not necessarily the case. We're very excited because in the next few years, with the advent of time outriggers, the ESA 2000, and other facilities, we're expecting that there will be 10,000 localized FRBs detected per year, which will enable these constraints. So this is something we're very excited about that we need to continue working on in preparation for these upcoming observations. So I'll just leave up. Thank you.
Thank you so much, Isa. Do we have any questions?
Thank you for the nice talk. Going back to this tight relation that you're finding, it looks like there is very little overlap between the simulations in the x-axis. So they are not probing exactly the same. I understand they are not probing the same regime. So how do you know that the relation is the same actually for the different simulations? Because maybe you follow the yellow points and it goes at lower regime to another. I don't know, just wondering.
I guess that's something where this is just demonstrating the correlation and indicating that we will just continue studying it. I think that's something that we find points that populate the whole.
All right, we can take one more question in the back here.
How dependent is this on your ability to correctly model the distribution of host galaxy DMs, and sort of like what types of simulations do you think you would need to be really confident that you were getting that distribution right?
In this current plot, we're ignoring host galaxy dispersion measures. We're looking at our DMs and using neuro solutions. We need to do like the DMs or DM growth contributions in simulations. There was a recent paper that also used CAMELS to look at DM growth contributions.
All right, thank you so much. Let's thank all of our speakers again today.